Another consequence and a beautiful example of this is the Foucault pendulum. And let me explain that. That is always given as an example of Coriolis force. This was one of the first demonstrations of showing very clearly how the earth rotates. So when considering this motion along the xy plane, suppose instead of letting the particle move along the xy plane, I tie it on a string and make a pendulum out of it. Then also it will keep moving along the surface of the earth. However, now it moves under two forces. The forces are, one, due to the tension in the string, and other due to Coriolis. So I am going to write d by dt of Vx. One term we have already seen is 2 m, or m, if I am considering force, then m has to be there, 2 m omega sine lambda Vy minus m omega square x, where omega square is nothing but g over L. And similarly, m d by dt of Vy is going to be 2 minus 2 m omega sine lambda Vx minus m omega square y. So the pendulum is going to swing with under the influence of these two forces, one the restoration force m omega square x, and the other the Coriolis force. And you can already see that because along when the Coriolis force acts, the ball tends to deviate, and therefore as the pendulum swings, you expect that its plane should deviate, should deviate from the path intended, and slowly it should rotate. The calculation of this would become easier if we consider r theta coordinate system. We are continuing with Foucault pendulum. In the xy plane, instead of using xy coordinate system, I am using r theta coordinate system, so that I can write that a r is equal to minus omega square r, where omega square is g over L without Coriolis force. But with the Coriolis force, I have an additional force which is equal to minus 2 m omega cross velocity, which I will write as minus 2 m omega sine lambda in z direction cross r dot in r direction plus r phi dot in phi direction. And this gives me minus 2 m omega sine lambda, z cross r is phi, so r dot in phi direction, and z cross phi is minus r, so plus 2 m omega sine lambda r phi dot in r direction. Notice if there was no Coriolis force, if there is no Coriolis force, then phi dot is 0. So no Coriolis force implies phi dot is equal to 0, and therefore phi dot we can expect to be of the order of omega. Therefore, in these two terms, omega times phi dot is going to be an order smaller than the first term. Let me write it clearly on the next page. We have f Coriolis equals minus 2 m omega sine lambda r dot phi plus 2 m omega sine lambda r phi dot along r direction, and this we are arguing is an order omega is smaller than the first term. So, I am approximating this to be 0. So, effectively this is the force. So, what does my equation including this becomes? It becomes m r double dot equals minus m omega square r, that is the restoration force, minus 2 m omega sine lambda r dot in phi direction. So, this should be r vector, and this I am going to write as m, r vector is r double dot plus r phi dot square in r direction, this is in r direction, plus m r phi double dot plus 2 r dot phi dot in phi direction, and that should be equal to minus m omega square r in r direction minus 2 m omega sine lambda r dot in phi direction. Again, as I argued earlier, phi dot square is of the order of omega square, so I am going to neglect it here, and therefore my equations of motion in the r and phi directions become, this m is also going to drop out. So, my equations become r double dot equals minus omega square r and r phi double dot plus 2 r dot phi dot equals minus 2 m omega sine lambda r dot. First equation gives me the usual oscillatory behavior with r equals some amplitude sine omega t. To solve the second equation, I multiply this whole thing by r to get r square phi double dot plus 2 r dot phi, this is phi dot is equal to minus 2 m omega sine lambda r dot, and this I can write as d by dt of r square phi dot equals minus d by dt of m omega sine lambda r square. A comparison gives me phi dot equals minus m omega sine lambda, and therefore, as the pendulum swings, its plane of oscillation keeps rotating backwards with a phi dot which is minus m omega sine lambda, and therefore, sorry, this m has dropped out, this m is not there, this m is not there, this m is not there, and therefore, phi dot is equal to minus omega sine lambda. So, it completes an entire cycle in 2 pi over omega sine lambda time the pendulum comes back to its original plane of oscillation. At lambda equals 0, that is equator, this time is infinity, and therefore, the plane never rotates. At lambda equals pi by 2, that is the poles, t equals 2 pi over lambda equals 24 hours. So, within 24 hours the plane comes back to its own. You can physically visualize this. if this is the plane of rotation and the Earth is rotating beneath it at the North Pole, the Earth comes back to its original position in 24 hours, and therefore we see sitting on Earth that the plane has come back to its original position in 24 hours. And as you go farther away from the poles, the time increases. So I have given you two examples of deflection of a particle moving along the surface of the Earth. One where I showed that x and y, when I give Vx, it tends to deflect in y direction, and another example which is the Foucault pendulum. A consequence of this deflection is that when you fire, say, a missile or a bomb over long distances, they tend to deflect from their intended target, and the correction for that has to be made. That correction has to be made because there is Coriolis force or the Earth moving underneath that moving target, so that it deflects from a straight line as far as seeing from the Earth is concerned. As the final example of the effect of Coriolis force, let us take a particle which is dropped from a height h and see how it deflects. In this case, this is omega. It has two components, one the vertical component, one component going towards the north, and you will see that omega v, the vertical component, cross v, because the particle is dropping straight down, is 0. So the deflection would come because of the omega horizontal. Let me call this omega horizontal, omega vertical cross v is not 0. So the forces that are acting on the particle are the mg vertically down and minus 2m omega cross v, and that we have already seen is nothing but minus 2m omega horizontal cross v, which is going to be, if I am at latitude lambda, minus 2 m omega cosine lambda times v, and this is going to be perpendicular to north direction and the vertical direction. So now if I were to write the equation of motion, I am going to have, let me call this direction the z direction. I am going to have d by dt of v is equal to minus mg z minus 2 m omega cross v, and up to the first order we have already seen, if the particle is coming down, this is going to be minus mg z minus 2 m omega cosine lambda v. This sign I am right now not writing clearly because I will talk in terms of west, north, east, north, south, west, east. So what we have figured is that if I have this Earth and the particle is coming down, only this component of omega matters, and omega cross v is coming. The Earth is rotating like this, east is going into the board, so this is east, west is coming out. So omega cross v is towards west, minus omega cross v is towards east. So the deflection due to the Coriolis force is going to be towards east. And what is the equation for that? We have d v towards east divided by dt is equal to 2 m omega cosine lambda z dot. Z dot is the velocity, which is nothing but 2 m omega cosine lambda, and to first approximation z dot is nothing but g t. Integrating this, we get v east to be equal to m omega cosine lambda g t square, and therefore this is nothing but d x towards east divided by dt. X comes out to be 1/3. Oh, sorry, again this m is not going to be there because now we are concerned only with the acceleration. 1/3 omega cosine of lambda g t cubed. So a particle dropped from a height tends to deflect towards east on the northern hemisphere. How much is the magnitude? So x equals 1/3 omega cosine lambda g t cubed. Lambda equals 0, x is maximum. Lambda equals pi by 2, that is at north or south pole, x is 0. So at the equator, if a particle is dropped from a height of 100 meters, you can calculate x, which is 1/3, omega is 7.3 times 10 raised to minus 5 times cosine lambda is 1, g is 9.8, this is going to be 200 divided by 9.8 raised to 3/2, that is the time cubed, and this comes out to be 2.2 centimeters. So you can see the effect is small but significant. If we go to the southern pole, omega cross v would change direction, and therefore the deflection would be westward. This concludes our lecture on the rotating frames and also our 2 lectures on motion in non-inertial frames. What I have tried to do in these 2 lectures is given you an idea as to how to deal with the motion in non-inertial frames. We can do many more complicated problems. The idea here was to just convey an idea, give you a feeling for non-inertial and pseudo forces.